All right. Good evening and welcome to another Visug evening. Today we're going to be talking about a topic that I think every C# developer will come across pretty much every day, and that's going to be async. We're going to get some internals. We're going to get a lot of insights, I think, into the asynchronous way of working in .NET. And the session is going to be by Adam Furmanek from Seattle.
Hello.
Hi, Adam. Before we get started, a little reminder that we already have the next session available, which is going to be on March the 23rd, again starting at 6. And that's going to be a double session by Khalid and Maarten. And you can already register for that on the Visug website. And it's, of course, going to be, again, an online session. If you're interested, we have quite a few interesting sessions lined up already, but we're always looking for new speaker talent. Let us know. We have an open Sessionize, so sessionize.com/Visug, where we're still looking for sessions. So let us know your proposals, and we'll be getting back to you to see if we can plan it and if it fits the agenda. And of course, we couldn't make all of this happen without our partners. So again, a big shout out to our partners also in these troubled times, make it possible for us to continue hosting our sessions. And so with that, I want to give the stage to Adam. I will stop sharing here, Adam, so you can now go ahead and start sharing and enjoy.
Well, thank you for this great introduction. So let's get down to it because we have plenty to cover and not that much time. The whole point, the whole idea of this talk is to understand this one simple but very counterintuitive sentence that throughout the entire process of applying, of using any asynchronous programming, a key takeaway is that there is literally no thread dedicated to running the task. And through this talk, we are going to see how it's possible that even though we have literally no threads, we are still capable of delivering some stuff. We are still able to do some job and run this whole machinery under the hood without any threads backing the tasks we are running. So this is the idea, and with this quote in mind, I'd like to introduce you to the internals of Async. My name is Adam Furmanek, as it was mentioned, and before we actually move on, a couple words about me. I'm a software development engineer with some 10 years of experience, also blogger and public speaker. I've written this book called .NET Internals Cookbook. If you're interested in internals of .NET platform, feel free to take a look at it. It's meant to be succinct, it's meant to be short, so it's a series of questions and answers, something like 100 questions about various .NET internals. So feel free to take a look at it if you are just looking for something which is giving you a very short, concise answer and pointing you to some other resources which where you can find some more details. Also, please, I encourage you to take a look at my blog at blog.adamfurmanek.pl. Feel free to drop me a line or email, Twitter, whatever works for you. And with all that, let's actually move on to the agenda of this talk. So the idea is we would like to understand how async and await works under the hood. We would like to understand why these mechanisms were introduced, what's the goal, what they are supposed to be solving. And we also would like to see how they were implemented. So we'll understand plenty of details and things which are deep inside the .NET platform. We will see some decompiled code. We will see some internals, some source code showing how these things are generated by the compiler. And the other, to understand all of these things, we actually need to start with some background, some historical understanding why this async even emerged. So we'll need to see some primitives which are backing the mechanisms under the hood. And then we'll need to focus on the task class, which is the bread and butter of this whole machinery. However, if you think that async and await is about async and await, that you may be surprised because it's all about the synchronization context, which is yet another part, actually even more important. And we'll see all its internals to understand why async may lead to multiple deadlocks, multiple issues, excess memory usage, and other things which we typically do not think about when we are just reading about this mechanism in tutorials or whatever. Finally, we'll see some compiled code or decompiled code which was generated by the compiler for us. And ultimately, after getting all this theoretical background, we will start looking at the issues and at the other things which may give you some more understanding of the mechanisms. we will see deadlocks, we will see how to actually handle exceptions, we will see how to capture threads for doing the work we'd like to do, and ultimately we'll finish the talk, we'll land with awaiting asynchronous void methods. So async void methods, will await them at the very end. That's the goal. Okay, let's move on. So primitives under the hood, because before we actually start talking about asynchronous programming, we need to understand that there must be some thread. There must be some machinery to run the code. We'll later understand why there is no thread when we are talking about asynchronous programming, but when we are dealing with the regular applications, there is always a thread. There must be a thread which we use to actually start our application and well, run the methods we are writing. So it's important to understand that under the .NET platform, there is a thing which is the operating system level thread, the native thread. And there are multiple types of these threads, like foreground and background threads. For us, what is important from this slide is that first, Windows schedules threads, not processes. This is important for scheduler, and this is important for performance as well, because depending on the scheduler you use and how you configure it, you may actually get longer pauses and slower, lower performance, depending on what you choose in your Windows operating system or in any operating system, right? Because the same applies for Linux or macOS. And other important part for us is that by default, the native thread, the user operating system level thread, by default, it allocates 1 megabyte of stack memory when the thread is created. Actually, a thread may have multiple stacks. It has at least 2 of them, one for user space, one for kernel space. On Windows 64-bit, when we are dealing with 32-bit applications, it gets another stack. And depending on the security principles and whether we are running on some fancy architectures, it may get something like 5 different stacks. However, for us, we typically focus on this user space stack only. An important part here is that on Windows, by default, it has 1 megabyte of pre-allocated memory when we create the thread. So now comes the trivia. How many threads does the Notepad.exe have? And the trivia comes from the typical conception that we say that, hey, threads are heavy. We should not be creating threads. So let's start Notepad here. So you can see I'm just creating a brand new Notepad, and I'm using Process Explorer to actually examine this application. So when we take a look, where is this Notepad? This magical Notepad is here. When I open the details, oh, they are on the other screen. There we go. And when we go to the threads, you can see that right after starting the application, there are 7 threads created. So we just started the Notepad.exe, and we already have 7 threads. Obviously, not all of them consume the same amount of memory because some of them are created in some lightweight mode, so they do not consume all that memory. But hey, just when we started the Notepad, it consumes a lot. But things are getting even more interesting. Like now I will hit Ctrl-O just to open a new file, and you can see that opening a new file created additional threads in the Notepad.exe. It has something like 18 threads currently just to open a file. So you can see that even the simple application Notepad.exe is actually very heavy in terms of how many threads it has. And they always tell you, do not create threads because, well, threads are heavy and they consume plenty of memory. Don't do that, but, well, this is how it comes. We just started the Notepad.exe and we have this many threads. Another trivia is actually how many threads are there in any .NET application when you started, and the answer is there are at least 2 different threads. One of them is the thread for you, for your application. The other thread is for garbage collector because GC runs on a separate thread. Actually, it runs finalizers on a separate thread. So there are at least 2 different threads. Your application is by definition always multi-threaded, which has some fancy consequences, like you may get erase conditions when you are exiting the application and cleaning up some resources, but we typically ignore this because, well, it happens. It's rare, but still it happens, and we typically do not think about that. But this is when it comes to the native threads. When it comes to the .NET application, on top of the native thread, there is always a thing called managed thread. So like a .NET thread, which is running on top of the native thread. It's important here, there are a couple things which we need to keep in mind. First, .NET threads, they do not pre-allocate the memory. So they are slightly lighter than native threads. So they do not commit this 1 megabyte of stack memory when we create them, but still they do allocate some memory. So they are heavy nevertheless. Second thing is, depending on what platform you run, killing a thread or actually having an unhandled exception on a thread may cause your application to be terminated entirely. So if you run, depending on whether you run on .NET, very old .NET frameworks like 1, or whether you run on new .NET Core, etc., unhandled exception kills your application, and this is what you should always assume. Always, whenever you create a new thread, like using constructor, always use try catch on top of that thread. Otherwise, unhandled exception will take your whole process down, and you cannot help that. You cannot stop this. Also, when it comes to threads, there was a nice method called thread.abort, which was deprecated between .NET Framework and .NET Core. It's now not supported. However, thread.abort was, we could use it to actually terminate the thread in a very direct, heavy manner. So we cannot do this anymore. Now we need to do some more of a cooperative scheduling to terminate threads, etc. But generally, depending on the platform, this may be enabled or may not. But there are actually two different things which are super useful, and I highly encourage you to always use them. First thing is the ID of the managed thread is different than the ID of the native thread. That's because depending on the configuration of your platform, one managed thread may actually be executed on multiple native threads. It can roam in theory, move between threads, move from one thread to the other, but this technically does not happen in the current implementation. But at the same time, the other thing which may happen is there may be multiple managed threads running on top of one operating system level thread, on one native thread. This is not guaranteed to never happen. Current implementation does not use it. However, there are multiple approaches to do that. Approaches with fibers or user level threads. So do not make an assumption that one managed thread, there is only one managed thread on top of one native thread, because it may be changed in the future, especially now in phase of the Project Loom in JVM world, which is trying to restructure the asynchronous programming and implement it in a much different way. So it may be that couple years from now, .NET goes similar direction and actually structures how it schedules the threads on top of the native thread. So do not assume that there is one managed thread on one native thread, because this can change. The other important thing is that we can name threads. So if we take a look at the debugger, there is a very nice column called name, which we can use to actually assign a name to the thread, just like in this code in here, thread.name equals custom name. This is super useful because first we can see this name in the debugger, and second, we can actually recognize what the thread is supposed to be doing, which is not necessarily the same as what the thread is actually doing, depending on, especially in terms of asynchronous programming and code moving from here to there, it's very easy for a thread to start running the code which it wasn't supposed to be running. So it's always a good idea to name the thread, so it's helpful for you during debugging. But we already mentioned, and you probably heard many times, that, hey, threads are heavy. And because of that, we do have a thing called thread pool. So thread pool is basically a static class in .NET, which provides you this machinery which holds multiple threads, and you can just post a work item to the thread pool, so it's being executed on any of the threads available. Actually, the thread pool in .NET is pretty complex, pretty sophisticated. It has fancy algorithm to create new threads and tear them down when they are not needed. It controls whether threads are long running, short running, etc., etc. Also, the same applies to the thread pool. Like the unhandled exception on a thread from a thread pool may take your application down. With current implementation, as far as I recall, it's not happening. Currently, it doesn't terminate your application, but it was changed at least twice during the .NET evolution, .NET development. So do not assume it's never going to happen. Always handle your exceptions. So the algorithm for thread pool, when to create a new item, etc., may be a little fancy, but because we are trying to understand internals and we will be re-implementing internals today, we would like to implement our custom thread pool. We cannot create a new instance of thread pool because it's a static class. However, implementation of a very basic thread pool is actually pretty trivial. That's all you need to have to implement a thread pool in .NET. So it's just like a blocking collection of lambdas which will be doing the job, and you have a collection of threads. You create threads and then iterate or for each the collection, enumerate the collection, and just run lambdas. So that's all you need. I'm not asking you to remember this code, obviously, but I'm asking you to remember that, hey, we know how to implement custom thread pool because we'll use it a little later. So this is when it comes to threads. And we know threads are heavy. We should not be creating threads. But hey, we always had this need to run some code on the side. We always wanted to have something, hey, just run this thing, execute it, and when you are done dealing with that, just let me know. So this is why there were multiple different patterns for asynchronous programming in .NET history, and one of them is called asynchronous programming model, APM for short. You can recognize this model because it has this typical pattern of two methods. One is begin something, the other method is end something. So you can actually schedule the work with begin whatever and provide a lambda which will be executed at some point. You can also wait for the completion by calling end operation, and that's it. That's all you need to do to actually run some work on the side. But that's not the only pattern which we have in .NET. The other one is called event-based asynchronous pattern. The short is EAP. So this one we use with the background worker, which is supposed, like we typically use it by applying lambda to the do work, assigning another lambda, and then this lambda is basically executed on a separate thread somewhere in the background. It can be canceled, can be used with like user interfaces, etc., etc. So there were multiple approaches how to implement asynchronous programming in .NET, how to make it nice and easy. And both of these patterns we have seen and other patterns of the time, they always share the same flaw, the same drawback, being that you need to basically assign some lambda which will do the job, but you cannot just carry this code with you. The code is not like a first-class citizen of the platform of your language. And that's how a task-based asynchronous pattern TAP emerged. So we wanted to have some notion of a piece of code to be executed somewhere, sometime by some machinery. And in the task-based world, this notion is basically the promise, which is the class task. So task is basically like a piece of machinery, piece of logic, which holds the code which we would like to execute somewhere. And you probably know there are methods like task run to actually start the work, and we can create tasks, we can join them with continue with, exceptions are handled, etc., etc. So there are many things associated with this task programming model, which is way different as compared to what we had before, because task-based programming model now puts the code we would like to execute in the first place. It puts the promise first. So now we can not only assign lambdas, which is cool, but we can also take like a snapshot of the code we would like to execute or the flow we would like to execute and pass it over, pass the task instance to some other method, and this other method can schedule some more continuations to this thing. And it's much easier to reason actually about the code flow because we have the continue with method. So we just put lambdas everywhere and it just works. The other nice thing about task programming model was that there was this thing called peeling, which is parallel language integrated queries, which, as you probably know, is a way of running or iterating over collections in parallel. So now we do not need to actually create threads or submit tasks to the thread pool or work items, take care of all this synchronization, nothing like this. we just do as parallel on any enumerable collection, and bang, now it runs on multiple threads, possibly improving the performance. So this is actually very, very nice way, because with just one method, we can introduce the parallelism, which is very cool when we take a look at it. However, there are actually multiple reasons which we don't like about tasks, and one of the reason, and not the most important one, even though it seems that it may be super significant, but it's actually not. We'll get to more important reasons later. But one reason also was that, hey, with this task continue with, we need to pass lambdas. Yes, we need to write lambda, 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 etc. But what if we would like to unwrap all these lambdas? And this is how async and await were introduced, because we can now await something which is awaitable, and we can write the code like it was completely synchronous, but under the hood, it's like scheduling all those lambdas and all that methods to do the job. However, it's important to understand that async and await can be used with anything which is awaitable, not necessarily a task. This can be anything which supports viaduct typing, supports things like this, actually supports a method called getAwaiter, which returns a type which implements couple fields, couple properties to check whether it's completed or to check whether it has a result. And we are actually going to see a very simple example in which we are actually awaiting integer. So you can see that here I am awaiting a number 2000, right? So I'm awaiting integer. This not only does compile, but also it works, because what I'm doing here below is I'm adding an extension method called getAwaiter, and I'm extending the integer to provide the getAwaiter method. And what I'm doing is I'm just running the task delay and getting its awaiter under the hood. So you can see that, hey, first it works because we waited for 2 seconds from here to here, and yeah, and it just compiles. It's as simple as that. Obviously, I'm not telling you that, hey, we should be now extending all our types in the code base to be able to await integers, something like this. I'm just trying to show you that, hey, this mechanism, it is pretty flexible, so it can be introduced to multiple types, not only to the task type. However, when it comes to the most important part of async code is we need to understand why we even have it. And the answer is the whole point of asynchronous code is that it does not block the operating system level thread. It can block something else. It is allowed to block in general, but we should never block the native thread. That's because when the native thread is blocked, then, hey, it cannot do anything useful. So it just wastes resources. We need to create the other thread to do some work. But if we do not block the thread, then this thread can go and do something else without actually us having a need to create a new thread, allocate some more and more memory. So that's the whole point of async programming, to never block the operating system level thread. And it has pretty significant consequences, and we'll see them through this talk. Just to give you a quick heads up how async in C# is implemented, it's implemented as a coroutine compiler level transformation, which is done by the compiler implementing the state machine for us, which we will see later under the hood, and using service locator for promise orchestrations. And this is basically the synchronization context, and with statically bound promise factories. And this is the type which we return from our method, which is task or value task typically, or something else. So we'll get through all these three elements during this talk and understand how they work together. So when it comes to statically bound promise factories, it's all about task. Because the task class is used with asynchronous programming, we are going to see how it's implemented. We're going to see why the task, this is bread and butter of whole machinery. And actually, there are two different types of tasks in .NET Platform, even though they are represented by the same class, the task class. Originally, it was used with this task programming model, which we have already seen with this pilling, etc. And this is the to support the CPU bound operations. So we just create a task which has some work to be done, some code to actually be executed. And we create tasks like this using the task factory or task run or whatever else, or just by as parallel in pilling, and they are scheduled and executed. They need to do some work. So they are tasks which actually go and calculate something. On the other hand, the same type, the task class, is being used for the asynchronous programming, for the IO-bound operations, for operations which only give us the promise that, hey, something will be done. Not necessarily something is going to be calculated, etc. But no, something will happen, something will be done at some point of time. For instance, this could be a delay. We are not calculating anything when we are waiting. We are just waiting for this thing to happen, for the time to pass by, and this is what task delay does. So even though we use exactly the same class, the usage is completely different, and the goal of when using task with async and await is way different than it used to be with CPU-bound operations. So just keep that in mind. CPU-bound operations are with the actual task doing some work, but IO-bound operations are with asynchronous programming. But in order to understand how the task works, we need to actually go through all these internals of the class, which were implemented starting in the TPL world. So we can actually divide them in like 3 different phases. First, we need to create a task. Second, we need to actually do some work with it. We whether need to wait, whether need to calculate something, etc. But actually, there is this phase of the task doing something. And ultimately, we need to clean up. We need to finish the task. We need to clean the resources, and we are going to see how these things work together. So the first phase is creating the task, and you can create the task with the constructor. And the rule of thumb is never do that. It was introduced to the platform, the ability to create a task using the constructor, because we wanted to decouple the part of capturing the code to be executed, wrapping it into some first-class citizen, and decouple it from the way of scheduling and running these things. So you could, in theory, prepare a task which would hold some code to be executed, and then pass it to someone else, return from your method, etc. And then this someone else would just go and decide how to execute this task, on what thread pool, on what factory, how to control like the newly created tasks continuations for that. So that was the idea, but we are not using that, and the rule of thumb is never use the constructor. In order to create a task, just go with task run or task factory start new or peeling, or just with async and await for the IO bound operations. So this is the way how we should be creating tasks. But we need to understand what is actually happening when we do the task run method. Because task run not only creates the task like with the constructor under the hood, but also starts scheduling it. So if we start decompiling the code, we can actually see that, hey, there is a nice method called schedule and start, and this method goes to the task scheduler here at the bottom and calls internal queue task on this task scheduler. And now we come to the other part, what this task scheduler is. And the same way we have the thread pool in .NET Platform, which is provided by the platform, which we cannot create an instance of, etc. Same goes with task scheduler. It is a static mechanism for scheduling tasks, making sure they run, etc. It supports multiple queues, multiple ways of like stealing the work, etc., and doing all these fancy operations to improve the performance. But again, because we would like to re-implement these things sooner or later, we need to see how to implement the task scheduler by ourselves. And we can see that this is the most basic implementation of task scheduler. And again, you can see that it seems to be pretty simple. We just have a collection of tasks, and what we do is we try executing inline tasks by inheriting from the task scheduler, and that's all we need. So again, I'm not asking you to remember how these things were implemented. I'm just asking you to remember that we can implement task scheduler. So we have already 2 building blocks now, thread pool and the task scheduler. So this is what happens when we create the task. It needs to be created, wrap some code, and then it needs to be scheduled and executed. But then we would like to actually schedule some continuations with this task. And this is where the continue with method comes into play. And this is the most important method of the task class. It has plenty of different options to control what happens with exceptions, to control whether we create a linear flow in our task, or whether we create a tree of our tasks, plenty different things to control fairness, to control asynchronous part of the code. But for us, the important thing is just use continue with, pass a lambda, and it just works. So this is how these things are handled under the hood. But when we start decompiling the code to see how these things work, the first thing we need to understand is when we pass the lambda to the task continue with, we create an object of the type standard task continuation. There may be different task continuations. We will see them a little later, but generally task continue with creates a standard task continuation. What it does later is that it calls the add task continuation method. So it basically goes to the task and puts the task continuation which you just created onto the internals of this task. So we can go through these internals, but the important part for us is what happens later when we would like to run this continuation. So at some point sooner or later, there is a method called complete. This method is called by something, whether it's called by the task because task finished calculating, or whether it's called by something else like IO bound operation, network driver stepped in and code complete. Hey, your network packages are ready to be processed by you, so I just call complete on this task. So when we call complete, the method try-set result is being executed. We go through a couple of internals to go through the state machine, but ultimately at the very end, we land in a method which is called finish continuations, and which goes to the task continuation, which we scheduled with task continue with, and it calls method run on the task. And this is the same method run which we execute when we create a task. So now we actually finish the run through the standard task continuation, and this standard task continuation creates or calls the methods schedule and start. So now you can see we close the loop, just like when we created the task with task run or task factory start new. We created the task and scheduled it and triggered it to start the work. So we basically called the method schedule and start. Now comes again the same thingy. We call task schedule and start on the continuation. So this loop goes on and on and on until we are finally done with all the tasks, with all the continuations. And now comes the question, hey, should we clean up tasks? And the answer is, depending on which platform you run on, the task may actually allocate something which is worth being cleaned up, or it may not allocate anything at all, because even though it implements the iDisposable interface, it does not mean that there is actually something to be cleaned up. So until .NET Framework 4, there was a thing called wait handle allocated, but calling dispose on a task was not a very good idea, because then the task was broken and you could not assign more continuations to it. So you were actually breaking the task when calling the dispose. Starting in .NET Framework 4.5 and on in .NET Core, there is no difference in the disposing the task, because it almost never allocates a thing. So there is nothing to be cleaned up. So the rule of thumb is never call dispose on your task, because you either break things or you don't do anything. So why bother? Not to mention that most programmers don't even think about cleaning the tasks, which is in this case is actually a good rule of thumb. So this is how we how we step through all these three stages of tasks, how we create them, how we attach continuations, and how we clean them up. There are a couple more important or useful things about the task. First is the status field, or the property of task is super misleading, because whenever you ask it whether it's completed, it will return you the true whenever it succeeded or whenever it failed. People generally think is completed as is succeeded, which is not necessarily the case here. So keep that in mind when using this property. The other thing is task.id. Documentation tells you that identifier of the task is unique. It's not true. You may get collisions with task IDs. So generally do not assume that ID is unique throughout your application execution. And one more important thing actually is that, hey, task is a class. It's heap allocated, meaning that it needs to be garbage collected at the very end. So it's very heavy, especially when we are talking about async and await machinery, because now almost every single method is await enabled. So you just put await everywhere. And this means that everywhere you create a task which needs to be cleaned up by the garbage collector, which is a heavy operation and takes some time. So generally, that it became an issue at some point. Microsoft realized it's not perfect, so they decided to introduce yet another type called value task, which actually complicated things even more. And I do have another talk called Async Biggest Mistake in C#, where I cover why the async is broken and why all these things are super heavy and should be re-implemented in a different way. But that's a digression, not part of this talk. However, to mitigate this excess memory usage, the value task can be used. And I won't be going much into the details of this class. I'm just giving you a heads up that, hey, if you would like to read about the value tasks, the structures which allow you to cut down on memory allocations, there is a very nice repository on github.com by Konrad Kokosa, which is called Put Value Task Source, which shows you how to do it properly so you cut the allocation as much as possible. And I also encourage you to take a look at Joe Duffy's blog post series blogging about Midori, which was an operating system in Microsoft, a research group where whole API, think about Win API, whole API was async enabled. So all the methods were async and await. So the task was passed throughout the operating system. So that's a very interesting read how they experimented with this machinery, especially that it influenced tasks in .NET heavily. So I encourage you to take a look at it. But that's all when it comes to the task type. Now we get actually to the second, even more important part of asynchronous programming or async in .NET, which is called synchronization context. And this is the global state for orchestrating the promise continuations. And we are going to see why it's important, what that is, and why it may lead to plenty of deadlocks in our applications if we are not careful. So the first thing is, as I mentioned initially, we always wanted to have this idea of, hey, I have some code, I would like to run it on the side. I don't care how, I don't really care when, just do it. Take this code, run it for me, let me know when it's done. So starting from the very beginning of .NET Platform, you had an interface called iSynchronize invoke, which was like an entry point for running things synchronously and asynchronously somewhere else. So this iSynchronize invoked was the machinery to do so. However, it had this, it was very coupled with the understanding with the notion of the thread under the hood. iSynchronize invoke was always tied to a thread. So while it was working and it was useful, we didn't necessarily want it to be that heavy. Like, we don't necessarily care whether it's run on some different thread. We don't want to think about synchronization, about mutexes, about anything else which is tied to that. What we would like to do is, hey, just take this code and run it somewhere for me. Do not create threads if it's not needed. Just reuse threads if they are available. So this is why iSynchronize invoke had to be extended to support some other machinery, and that's how synchronization context started. And the synchronization context is just one part of this whole code execution. When we think about code, we also take a couple things for granted and we do not dwell upon them. Some of them are like code permissions. Hey, can I actually run this code? Maybe this code is unsafe. Maybe this code is accessing some resources I should not be touching because, well, I'm not elevated, right? Maybe some code is carrying some other username. We are impersonating somewhere like on the web pool, like web request we are running in context of different user, right? So this should be carried with the code as well. Maybe there are some local variables which are tied to the thread, like thread local, like thread static, etc. They should follow the execution as well. So there are multiple contexts which take care of all these things, like logical context, security context, etc. And one of these contexts is basically the synchronization context. It's a bag which holds the details of how to capture and schedule the continuations which were triggered from a given point of time and given place in the source code. So there are multiple synchronization contexts. We'll skip this thingy. And the synchronization context is just like iSynchronize invoke was an entry point for running something on a thread. Synchronization context is an entry point to run something somewhere without necessarily specifying how, where, when, and in what way. So it's like a very lightweight abstraction of the idea of running a code at some point on a side. It provides couple methods like to send or to post methods, post messages, but gives literally no guarantees whether it will be executed synchronously, asynchronously, in given order, on a best effort basis, nothing like this. So we cannot assume anything about the synchronization context, but we do know that it's the right entry point for us to run something on the side. And as with everything, the important part is to understand how it works. And this comes the most important sentence of this talk, I believe, which is when awaiting the awaitable type. So when doing await yada yada, the current context, current synchronization context is captured. Later, the rest of the method is posted on the context, meaning that whenever you call await on a method, the context you are running in is captured, and the continuation, when it's time to schedule it and time to run it, will go through that synchronization context. So the synchronization context decides how the continuation is going to be executed, triggered, and when it's going to happen. We can stop this capturing by calling configure await false, and as a rule of thumb, if you're running some library code, you should always use it. Always call configure await false and never capture the synchronization context. Otherwise, you will get plenty of deadlocks. Capture the context only when you are sure, when you are aware of what you're doing, and you are positive you need that context. It may depend on the application you're running on type of application, whether it's console, web application, UI application, maybe it's some fancy framework or CMS or whatever else. In these cases, you need to understand what context you are dealing with. But generally, when you are writing like business code, which is not dealing with external world, which you could say is a pure code doing just pure calculations, etc., configure await false should be the way to go, almost always. When it comes to some internal, synchronization context is a global variable. There is synchronization context.current, which is captured. We'll see that a little later on. And if there is no context in our application, we'll see when it can happen, then the task scheduler is being used. So we'll say that we use the task scheduler synchronization context, even though technically there is no synchronization context at all. It's important to understand that each method can control whether it captures the context or not. So we can control this on a very granular basis. And the important part is there are multiple different contexts in our applications depending on where we are running. In console applications, like the default thread pool-based synchronization context, meaning there is no synchronization context at all, is a machinery which can execute your code on basically any thread in the thread pool, does not execute them serially, does not maintain the order, etc., etc. However, when we move on to the ASP.NET world, so like web applications, this is actually important for us to understand that, hey, when we run some code, we would like to be running that code in the context of the current HTTP request we are executing in, right? Because there is some network call which we are dealing with. So we would like to be able to access this network call. So the synchronization context in the legacy ASP.NET was actually taking care of propagating this network call throughout the whole code you are running. It was changed in ASP.NET Core. There is no web request like web context anymore. Like technically there is under the hood, but it's much, much harder to get to access it because there is no synchronization context which would be propagating this thing for you. However, when it comes to desktop applications or applications with user interface, and it could be something old as WinForms or WPF, but it could be also Xamarin or Blazor currently, there is a synchronization context which is based on exactly one thread, is backed by one thread, and only this one single thread can execute the continuations, meaning that whenever you await something, the continuation will need to be scheduled on the same thread where it started. And this may lead to multiple deadlocks. The important thing here is that the synchronization context is a global variable. So you may change it without actually realizing that it was changed. And the code which worked in one context may stop working in the other one. So this is what we are actually dealing with. And let's see how it works under the hood. And in order to do that, we need to see the very last piece of the asynchronous programming, which is the state machine generated by the compiler. And we'll quickly go through one method and to see what code is generated. And then we'll get to all the examples to see how these things work together. So we start with a very simple method, and what we'll would like to do is, this is the method here, which we would like to execute. Important part here is that it has 4 logical parts, like separate with different await keywords, right? So we do have 3 different awaits here, which in turn generates like 4 different logical parts. And we can see there is async here modifier, so this method is async enabled. We'd like to see how it works. So what we are doing is we would like to compile this code using C# compiler, and then we would like to decompile this code. Okay, so right after the compilation, first thing which we would like to understand is when we decompile this whole code, we can see that after the compilation, I'm just showing you the screenshot, it has like 130 lines. It becomes very, very long, even though our method was something like, I don't know, 10 lines of code. It basically explodes in the numbers, in terms of number of lines of code. So the things which we need to understand is, the first thing right after the compilation is there is no async anymore. Async is just for C# language, not for .NET platform. So there is no more async on the intermediate language level. On the other hand, what we create in this method is a very fancy type called program our async method the__1. Okay, so this is a type which will schedule, which will orchestrate all these details to handle the asynchronous programming here. And there are a couple important things here. One of them being the state. The state is pre-initialized to value -1. We'll see later what's going on with that. But then there is a method start called on the instance of this type. We'll see to what the start method does, but it's important to understand that at the very end, we just return the task. That's it. We enter the method, we set the state, we call the method start, and then we return the task. So this is how we need to understand what's going on under the hood. And in order to see that, let's carry on. So the type which is being created, it actually has multiple fields. One of them we already seen is a state, integer state indicating where we are. There is some builder to tie things together. We won't be getting into that, but there are also 3 different awaiters here. You recall the original method had 3 different await keywords. There was task from result, task delay, and task yield. And you can see the same things here. There is awaiter for task from result, the awaiter for task delay, and the awaiter for task yield. So there are multiple different awaiters here to back every single await keyword we had in our method. So this is where we start. And on this type, there is a method called start, which I told you that we call this method directly when inside this asynchronous method. And what this method does, it calls the move next method. The important thing here to note is that it doesn't matter whether you call await some method, the async enabled method, we are executing this method synchronously. This is important. We start executing it right away, and we get to the move next method under the hood. And let's see what this move next method does. What is actually the way it's structured is, first it gets this state field, which we pre-initialize to -1, and then it has try catch block. And you can see that catch handles everything, like handles all the exceptions, sets some states, some exception. These are like minor details, but it's important to understand that once you put async on a method, there is always try catch in this method. It always handles this exception to be able to propagate it later as necessary. But let's now examine what's happening, what's going on in this try method, because this is the actual meat, the actual machinery of the code we are running. And if we decompile it, we can actually see that there is a big switch statement in this method. And if we see what these things are doing, we can see that we had 4 logical parts of the method, like 3 awaits and 4 logical blocks. And these blocks are connected like this. So the block number 1 is like in these 2 places, number 2 is in these 2 places, etc., etc. And there are also go-tos, so there are jumps between these blocks of code. So let's now move on through these blocks and understand how they work together. So the first thing is we are running the code, and just before the await task from result false. It's important to understand that we enter the method with the num being initialized to the state, so it's set to -1. So we check all the cases. There is no case for -1, so we do not do this. We go here to the default thingy, and you can see that we are printing something and then getting the awaiter from the task from result of Boolean. And then we check whether whether the is completed is set to true. And the whole point of task from result method is, well, it's true because the task from result is always ready, always completed, right? So what we do next is we change the state to 0, we store some awaiter, etc. We are not doing that because we are not entering this if. Sorry for misleading here. We check whether is completed is set to true, and because it's false, we do not enter this if. We just carry on, and we call this get result on this awaiter. Okay, so you can see even though we did call await task from result, there is no context switch. There is no blocking, no waiting, just because, hey, the result is already available. So the asynchronous operation may flow synchronously, and this is what happens in this case. So we carry on from starting from line 72, and we get to the other block of this code, which is just before the await task delay. So we are in this line 72 here. So what we do now is we print, we again get awaiter, and we check whether this awaiter is completed or not. And in this case, because this is task delay, the whole point of task delay is to wait. So it's not completed yet. So we store the state to some magical integer 1. We store the awaiter, and then what we do is we call await unsafe uncompleted, and then we return. So let's see what this await unsafe uncompleted does. So when we go through this await unsafe uncompleted, we get the thing called get completion action. And this completion action is going to wrap the continuation of our method, so the code which we would like to execute later, and puts it on the awaiter object here. When we start debugging through these things more and more and more, we actually get to the get completion action, which creates an object of type move next runner. We have already seen the method move next, so we may guess what this move next runner is going to be doing. But at the very end, what is ultimately important for us that, hey, is just calling invoke move next. So this thing is a callback, which is then used to call the move next method, the same method where we started, because we were in the move next method, which called the we were in start method, which called move next method, and this is the method where we have this big switch. So we are actually trying to code exactly the same method again. What happens next is we just set the continuation on the task. So the task which we are executing, the task we are returning from the method, is going to be prepared with this continuation. So we do set continuation for await. Now we already know the other side of the story, because when we set the continuation for await, I already told you that the synchronization context is captured. And this is the place where this is happening. When we call the await something and we see the awaiter is not completed yet, we check whether we do have the synchronization context. If we do, then we capture the synchronization context for the continuation. Otherwise, we capture the task scheduler, right? So there is this no synchronization context case, and then we basically call add task continuation. And this is method which we have already seen, because this is the pure TPL world, the task method. And out the very end, we know there is some complete method code on the task, which in turn comes, steps in, runs the run method on the continuation. And this run method on continuation goes and runs callback. And this runs callback at the very end goes to the captured synchronization context here and calls the post method. So now it's the second loop of this whole machinery. The first loop was we create a task, it's scheduled, it has the continuation. When the complete method is finished, it calls the run on continuation, we are done. Here we have another loop, which is basically we start with capturing synchronization context, create a standard task continuation, which handles the synchronization context. When we start method on this continuation, the run method, it goes to the synchronization context and posts the continuation. The continuation here is the type of move next runner. So the move next runner is basically the object which at the very end calls the move next method. So now when we go back through slides, what happens is we called this await unsafe uncompleted, and this captured the synchronization context, prepared the continuation, and then we just return. Nothing else happens. We return here. Because we return here, we can continue unwinding the task, and we get to this, not to this method, to this method. Because we returned from the move next and we returned from the stack, from the start method, what happens now is we just return the task. So we return the promise, which is doing the magic of us being able to orchestrate these things. So you can see that await does not necessarily forces the context switch. It may execute things synchronously, but if it cannot execute them synchronously because they are not ready yet, it schedules the continuation of the synchronization context and then returns the task. So at some point, the move next runner is being called again, and this move next runner is basically calling exactly the same method move next. So we enter this method again, we extract the state field, and then we enter the try block. And the try block, we remember, is this big switch code. So we enter executing the same method again from the very top. So previously we exited here, and now we are entering here at this point, and we check the switch, the state. And the state is now set to 1, because this is how we set the state before exiting this method. So we execute this case statement, which is getting the awaiter, which is basically restoring the state, and then jumping from here to exactly this label. So this is how we do it. We execute the same method multiple times, only we jump through this method, and we do not execute it like it line by line. We jump and reorganize these things. So we finally, after returning to this method, we end in this line and we call get result. And because it's already after the task delay finished, we have the result and it's already done. So we can carry on from line 84. So we can skip all these slides. We carry on from line 84. So we carry on from here. And what we do next is we just print things. We get the awaiter. We check whether it's completed. Again, if it's not completed, and it's not completed because, hey, this is task yield now. Task yield posts the things for synchronization context, which is not super important for us. But the important part is at some point, when we return here, we set the state to 2, and then we enter the switch construct again. So we execute this piece of code, and ultimately we jump again over these lines to this label. So this is what we do over and over and over again. We set the continuation, store the state, then the same method is being called again. It does the switch construct, jumps to correct place, and we carry on. Ultimately, at the very end, we have the last part of this method after last await, which was just throwing the exception. And I already told you that there is a try catch block spanning this whole code. So this exception is being handled immediately inside this method. It cannot escape this method. So this is how it works. This is how it's constructed. And this exception is later stored on the task object. A couple other things which we'll quickly move on, depending whether you are running this in debug or release. This is either a class or a structure to improve the performance. And the difference between async task and async void is the different builder which we use. And depending on the exception type we have, whether there was an exception or not, the exception is either stored on the task or propagated asynchronously. We will see that in a sec. Okay, so this we can skip. And now we have everything to actually understand what there are deadlocks in the application and why synchronization context is important and how to await async void methods. So let's go through all these parts to conclude this talk and use the knowledge we just get to do some fancy stuff. So first thing is, because there is no thread waiting or actually doing the job, or the thread is not observing these things, we may actually get deadlock just with one thread triggering the operation. And the rule of thumb is always use the async all the way up and configure await false all the way down. Never wait synchronously for tasks. Why? Because you will get deadlock, and we'll see that in a sec. Let's imagine that we have this a very simple example of a code, so we'll understand how the synchronization context is captured. So we start here. And we already know that when we call await process data async, imagine that this is some UI application like WinForms, Xamarin, Blazor, doesn't matter, right? We just enter with the synchronization context, which is backed by one thread. So we enter the await process data async, and we already know that this starts executing the method synchronously. So we go here, and what we do here is we call await download async, we call configure await false. So if this download async finishes synchronously, then the continuation of this method, namely this part of the code, is executed synchronously right away on the same UI thread where we started. But if it's not finished synchronously, then because we code configure await false, we do not capture the synchronization context. So this continuation is being executed on a thread pool. So it's not executed on the UI thread anymore, but on a thread pool thread. So it is executed somewhere else. The same goes here. We also call await something and configure await false. So we do not have the synchronization context. So this very last line of this method, the continuation, is executed on a thread pool. However, because here at this point, we did not call configure await false, then the continuation from here being this part of code did capture the synchronization context. So the line result textbox.text is being executed on the UI thread again. And this may cause a deadlock depending on the type of application we execute. So let's see why. If we start with this piece of code, which is a console application. What we do here is we call some async method and we synchronously call .wait. So in this async method, we do await task delay and we do not call configure await false, but because there is no synchronization context in console applications, the last line of this method is executed on some completely different thread, on a thread pool thread, right? So even though this thing here is blocked, this continuation ultimately finishes. So this whole code continues and you can see on the right side that, hey, it's done, it did work, right? However, if we take exactly the same code and move on to the UI application, we get something completely different. Why? Because if we call the operational context and call synchronous.wait, then the continuation after the await task delay was to run on the UI thread because there is a synchronization context. And because UI thread is waiting in this .wait, it is generating a deadlock because this continuation never gets a thread to be executed on because this thread is waiting here on the continuation to be finished. So it's a classical deadlock with just one thread running the code. How do we solve that? Well, there is a simple solution, seemingly simple solution. We'll just run configure await false. So now this continuation this continuation can be executed on a thread pool thread. So even though we block the user interface, we freeze it for 1 second, right? Because we sleep for 1 second here. After this 1 second, the continuation finishes and this whole UI thread can be unblocked, can continue. So it seems like adding configure await false when we are dealing with synchronous wait on async operations is actually the solution. Unfortunately, it's not always the case because, hey, depending on the application type, it may not help you. Because imagine now that the continuation would like to explicitly go to the UI thread and do something. So we just call invoke, and this Lambda would like to be executed on the UI thread. But again, UI thread is deadlocked because it's waiting on the .wait operation, so we cannot deal with that. So again, the rule of thumb is never block, not only never block the thread, the UI thread, but also never wait for async operations by calling .wait, .result, or .getAwaiter, getResult, or whatever else. Never do that. Have async all the way up. How do we fix this? Well, there is a simple hacky solution. I'm showing it to you just for the sake of completeness. Instead of waiting synchronously, what we can do is we can do the speed wait. So we can wait for a millisecond and check whether there is a message in the UI thread message queue. And if there is one, this message at some point, the invoke method will post a message which will execute here at the do event. So even though the UI thread will be frozen for 1 second, at least it will work and it will continue after this 1 second of very bad experience, very bad user interface, right? So we can hack these things. And if we are dealing with asynchronous methods from a synchronous context, this is actually what we need to do. We need to introduce hacks like this. But the story goes on. You need to have configure await false all the way down. Why is that? Imagine that we have this code. So we call method wait1 and we call synchronous getAwait or getResult, okay? So we call wait1 and what we do here is we await wait2, but we do not capture the context, okay? Then we await wait2, sorry, in wait2, we call await wait3, but we do capture the synchronization context, and wait3 ultimately waits here and does not capture the context. So what happens is the user interface is blocked again because, hey, the UI thread is stuck here in this synchronous operation, right? But after 1 second, the continuation from here is being executed. And because we did not capture the synchronization context, it is executed on some thread pool thread. So we have a thread to execute the continuation. So it just works, right? So we finish this method. This method is now done. So we carry on in here. But because this thing did capture the synchronization context, because the synchronization context is at this point. Why? Because we execute this method starting from here. We execute this method synchronously, and we enter this wait too. So we execute this method synchronously. So we do have a synchronization context at this point. Then this continuation here would like to be executed on the UI thread. And what does the UI thread do? Well, it's being blocked in the getAwaiter.getResult. So you need to have async all the way up and configure await false all the way down in order to avoid these deadlocks. So these are rule of thumbs you need to follow. There is yet another nice thingy. Imagine that you are actually doing this unit test and you are creating a new form of win forms, right? So what is happening here? Like, obviously, we never create user controls in unit tests, right? But sometimes the people do that things, right? So what is happening here is this test never finishes. Why is that? That is because the continuation after await task delay, it did capture the synchronization context because there is no configure await false, okay? But the synchronization context for this thingy is a synchronization context which is different than the one we started the method with. Because here at this point, we have the NUnit synchronization context, but then this new form goes and initializes the WinForms framework and replaces the global synchronization context variable so changes it. So how can we deal with that? Well, we can get the global synchronization context, store it in the variable, and then after creating this new form, we can restore the synchronization context. Yet another hack to deal with this global state, which is hidden under the hood. This thing will skip and we'll carry on with exception handling. So when it comes to exception handling, this is yet another part. After dealing with all the deadlocks we had in our application, now we need to handle exceptions. So what we can do is we need to understand that exceptions in async void methods are propagated non-deterministically, and they are propagated in the out-of-band manner. However, in the task method, they are stored on the task object. So what we can see is we'll actually see this in action. So we will go to see some code, and I believe this should be it. So exceptions in async. So what we are doing here is, let me just select the proper project so we can execute this code. Okay, so we are here in this method, and what we do here is we do have a very simple method called throw, and this method waits for 300 milliseconds and throws the exception. Okay, so we call this method, and this is an async void method. So we call this method twice from the try catch block, and we try to handle this exception here. So what you can see after running this application, well, it seems like it did work because we can see that this done line is being printed out. Okay, so the application did crash, did print this exception, but seems like, okay, it finished execution, so nothing bad. But let's see what happens if we introduce some random delay in the middle. So because now this throw method is waiting for 300 milliseconds, and we are waiting here like 5 times longer, maybe this time this exception will be handled by the catch block, right? So let's see what happens now. And not only we cannot catch this exception, also the application crashed, and not to mention that at the very end, it did not print out the done line, okay? So just by adding random sleep somewhere in the middle, we actually changed the behavior of the application significantly. So, and we cannot handle this exception. So what happens is, if you do deal with async void methods, make sure that you always handle the exceptions, otherwise they will kill your application. But what happens if we change this async void method to async task method? The difference is that this time this exception is not propagated, is not printed out, it's stored on the exception on the task object, and effectively is lost for us. We cannot extract it anymore. So this is what happens with the async tasks, with tasks which you do not await. And if our Visual Studio tells you, hey, you should be awaiting this call, because it's not awaited, then you get a synchronous thingy and you may get some issues. So this is how you need to deal with exceptions. Never use async async void methods and always await tasks. But things are getting a little trickier because exceptions in other threads, we told you that they may kill your application. So always do have this try catch handler. Otherwise, if you do not have it, just like with async void, it will kill your application and you cannot deal with that. There are tricks, there are hacks to do that, but we won't be getting into these hacks today. However, feel free to take a look at my blog. I show you how to actually handle all these exceptions, but this is not the main point of this presentation. But there's yet another thing when we are dealing with TPL world when it comes to stacking exceptions. So if you remember the TPL, you could run continue with method, and in continue with you could specify whether you want the continuation to be executed like linearly or whether you wanted to have a tree of different continuations executed. And now, depending if you wait for the task using .wait or using await, you get a different behavior with exceptions. See what we are doing here. I'm calling await create task. And in this task, I'm returning a task which creates two child tasks which are attached to parent, and both of them, they throw exception. So if we now await this task, what happens is we get only one exception. This exception is, the second exception is lost. Not to mention that we don't know which exception will be handled. How can we extract both of these exceptions? The answer is we actually need to go with this old thingy called continue with and specify whether the continuation needs to be run on completion or run when the exception happened, when the exception appeared. So this is what we need to do. And if we do that, then we can see that, hey, there is second task exception here and second task exception printed out here, and there is a first task exception, okay? So if you are dealing with sophisticated tasks, you cannot go with await because await handles one exception only and loses all the others. So we mentioned many times already that we can lose these exceptions. Is there a way to retrieve them somehow? And there is actually a way to retrieve them. And this thingy is called the unobserved task exception. So whenever there is an exception on a task, and this task is being garbage collected, the garbage collector will clean up the task and will propagate the exception for you. Notice what I'm doing here. I'm adding a lambda on the task scheduler unobserved task exception, and I code a method test which basically thrown the exception, and then I'm waiting for read line. You can see there is no exception printed out. But once I hit enter in the application, the garbage collection will be forced by calling gc.collect, and you can see that my handler was executed. So this console write line was executed here. So this exception may be propagated later in the out-of-band manner by the garbage collector. And depending on, again, configuration of your application, it may or may not kill it. Current implementation, as far as I recall, is it does not kill the application. However, it was also changed between different .NET versions. So keep that in mind. Always await your tasks. Always have this handler to handle the exceptions and do not let them disappear. So this is when it comes to handling the exceptions. This is when it comes to dealing with the exceptions. And now we can use all the knowledge we have to actually await async void methods. So we said that, hey, async void methods cannot be awaited. But why is that? They cannot be awaited because they do not return the task, right? We need to have something which is awaitable to await and to wait for the execution. On the other hand, we can actually re-implement plenty of different things under the hood. And let me just select correct project, which is catch async void. And when we start this application, let's see what we are doing. So first, we do have a method, which is async void, which basically waits for a second and then throws the exception. And we would like to handle this exception. We would like to be able to not only not crash the application, but safely carry on with the execution. So the first thing we need to implement is we need to create our custom task scheduler, the same scheduler I shown you early in this talk. So we just have a collection of tasks, etc. Nothing big here, but we need to have custom task scheduler. Then we implement custom synchronization context. And this custom synchronization context uses our new scheduler. And it also creates a new factory for the tasks. And the important thing here is it hides the default scheduler provided by the .NET platform and instead uses our custom scheduler. Okay? Then on the synchronization context, we have a method post and method send to handle the lambdas. And we have two callbacks, operation started, operation completed, which we can just use to count the operations which are executed. Okay? What we ultimately need to do is we will be running our method, which we would like to await, not just like calling throw, but we will ask the helper method of our synchronization context, hey, run this method throw for us. And this synchronization context, what it will do is first, we take the current synchronization context, we replace it with our custom one, we create a new task for the lambda which we want to execute, and we run it through our task factory and task scheduler. And ultimately, we go through all the tasks which are scheduled through our task scheduler, and we execute them one by one, and we await for their to finish execution. So if anything is being added as a continuation, it will be added through our scheduler. So it will be added to this collection of tasks, and will for each until this whole collection is empty, and it will be marked as empty when all the operations are finished and the operations count is set to 0. Then we set the complete adding, so then we will exit this for each loop. Finally, we restore the synchronization context, and notice what we do here in this method. We just return a task. And this task we can use here. So we can take this task, we can assign it to variable, and then we can do whatever we want to do with it. We can call .wait, .result, await it. We can call get await or get result. That's all. And ultimately, we just print that we swallow the exception, and we have the sleep at the very end. So you can see that there was swallowing exception, there was some exception left from async void, there was sleep, and ultimately there is done line printed at the very end. So this is the way to handle and to catch and to await async void methods to do all the magic. And just to summarize, you need to know your synchronization context. Otherwise, you may get deadlocks a lot. You may break your applications. Do not use async void methods if you do not have to. Have async all the way up, always. Have configure await false all the way down. Avoid creating custom threads because they are heavy. Always await tasks, always handle the exceptions, always have the handler for non-observed exceptions, etc., etc. And with all that being said, it's good time to answer the questions you may have. So are there any questions I could answer?
All right. Thank you, Adam. That was mind-blowing, I must say. I was following, but yeah. Actually, so far, no questions. So I forgot to mention this in the beginning. So if there are any questions, you can post them in the Q&A window. So there's inside of this window, there's a Q&A on the right. You can also post them in the chat, but preferably in the Q&A window. So no questions yet, so we'll wait a couple more seconds.
Cool. So in the meantime, let's go through the references, and then we can handle the exceptions if there are any. So when it comes, if you'd like to learn more about the things I've shown you today, I recommend a couple books for you describing various .NET internals and Windows internals. So starting from the highest low level to the lowest low level, well, you can start with CLR via C#. And then you actually need to understand how the user mode works, etc., etc. I highly recommend actually taking a look at advanced .NET and advanced Windows debugging. And I also encourage you to take a look at this blog. If you would like to learn a couple fun facts or interesting things about like low-level stuff, Raymond Chen is the author of the Old New Thing blog, which is super interesting for that. If you would like to read more about the things I covered, a couple links pointing to my blog showing you things about the internals of async and other things. I also encourage you to take a look at my blog for other things, as I cover a lot about .NET. But if you would like to read things on the internet but outside of my blog, a couple useful links for you to see how these things are implemented. And you can get the slides even using either using this QR code, or you can just go to my blog, Adam Furmanek PO, and there you'll find all these things. And being that said, let's return to questions. So I can see two questions here. First is by Johnny Huybergs. Can I stop, cancel, kill a task without using the cancellation token? This is a very good question, actually. Before answering that, let's understand what a cancellation token does, because this is maybe very misleading for some people. When you cancel a cancellation token, it does not stop the task. It must be done on a cooperative scheduling manner, meaning that the task must ask the cancellation token, hey, are you canceled? If you are, then the task must exit by itself. It's not terminated automatically. And to answer this question, can I stop, cancel, kill a task without using the cancellation token? Even with using the cancellation token, you cannot do this if the task doesn't ask that. But without using it, I do not know if there is any way. I tried doing that, I tried Googling, and I do believe there is no nice, readable, easy way to do it. There may be some hacks like you could queue the whole thread running the task, but there is no clean way to stop one particular task. At least I'm not aware of any. This is actually similar to current state of threads, right? I mentioned that there is thread abort method, which was deprecated with .NET Core. Currently, you cannot forcefully terminate a thread. You could do it before, you cannot do it anymore because it's always risky, always dangerous. So I don't think there will ever be a nice, clean way supported by .NET Platform to actually stop a task. If this does not answer your question, feel free to elaborate more and we can answer that. And I will move on to another question by Aran Kandaswamy. Please forgive me if I'm pronouncing that incorrectly. What locks can be used with await? This is actually a super interesting question because the answer is no locks. Technically, no locks can be used with await because await can migrate from one thread to the other, and you have no idea where this thing is going to be used. You cannot, for instance, use the lock keyword inside the async method. Like compiler will not let you do that. You can use them like manually because lock keyword is just monitor enter, right? Or you could use operating system mutex or operating system semaphore, right? You could acquire them and then do something in async and await. And this is going to crash your application because if you switch thread to some other, well, then it's going to break because you won't be able to release the lock. Not to mention that if you take a lock inside the async method, then once you hit the await and you need to wait, you actually know that you return this method because you return task. So because you return, then probably your try finally block is going to release the lock for you, and you basically exit the critical section. So no reasonable the old way locks can work with locking, with async mechanism. However, you can implement your custom locks, and there are libraries for doing that. For instance, there is Async X library by Stephen Cleary, I believe, which provides you a couple of custom mechanisms. So you have async mutex or async lock, etc. But so you can do some locking with asynchronous code, but you cannot use the regular mechanisms for doing that. Hope that answers your question. If it does not, feel free to elaborate. We can dwell upon it a little more. There is another question by Johnny. How does semaphore slim work for locking? And that is a very good question. I actually don't know. I never took a peek into how it's implemented under the hood. And I don't know if it works or not. My guess would be it does not because it's. I believe Semaphore Slim was there before the async programming, and in that case, it's probably not supporting asynchronous context. But I cannot tell for sure. If it's implemented the old way, then it doesn't work. If it's implemented in having asynchronous context in mind, that it probably uses some execution context to pass data, just like this in this async X library. Because just like we have the thread local variables, we may have async local variables, which are propagated between asynchronous execution contexts. So we can store some data, some variables to support your locking. So generally, these locks, if they do work with async and await, they do use async local variables to store the data. But as I said, for the particular thingy with Semaphore Slim, I do not know. Are there any? This is answered. There is yet another question by Daniel. Is there a rule of thumb to know what synchronization context is being used? How am I supposed to know the UI context is being used? Or when do you not need to use the configure await false? That's actually a very good question. How do you know that? You should generally understand what type of application you are running, okay? If you are running desktop app, odds are you do have synchronization context. If you are running console application, most likely you do not have it. If you are running a new ASP.NET Core web application, which is not Blazor, then you do not have synchronization context, most likely. Something can step in and replace the context for you, but generally people do not do that. So if you know the type of the application you are running, then you should be good to go. However, it's actually interesting as well, because if you are using some CMS, or if you are using some custom framework like Episerver or Sitefinity or Sitecore, do you know how does it use the synchronization context? Personally, I do not know. And this is important because the synchronization context may be used, for instance, for database operations in some way, right? So in that case, you need to reach out to the documentation. And the second part of the question is, when do you not need to use configure await false? Generally, the rule of thumb is, if you are in your business logic project, then you do use configure await false, meaning like you have a project code, I don't know, domain, core, something like this. You do use configure await false there because you do not want to capture the synchronization context at any point of time, because you don't need it. That's the assumption. Obviously, if you do need it, you need to capture it, but you probably don't need it. But if you are in the upper layer of your application, like the user interface, presentation, model view model, the view model part, etc., there you probably need the synchronization context. So in that case, you should not be using configure await false, or you may consider not using configure await false because you may need this context. Obviously, this question is very hard to answer because, hey, it's up to you, and it's your responsibility to understand what type of application you're running. I cannot answer that without seeing the source code because I don't know what synchronization context you may be needing. But the rule of thumb is business logic, configure await false. User interface, do not configure await false because you may need this context, but ultimately you need to know whether you need it or not. I do not see any other questions.
We are through the questions. We are nice on time. Adam, that was super interesting. A real big thank you for doing this for the user group. Yeah, I hope everyone enjoyed it. And so we'll see you again end of March for the next session. Thank you.
Thank you.